Hello everyone, today I'll be presenting learning decision-making strategies of non-experts, a next-scale model for taxi drivers. My name is Xin Zhang. This is a joint work with Dr. Menghai Pan, Professor Yanhua Li, Professor Xun Zhou, and Dr. Jun Luo. Massive spatial temporal data are being generated by humans in the urban environment every day. For example, GPS trajectories collected from taxis and personal vehicles, passenger trip data from automated fare collection devices on buses and trains, and working traces from the emerging gig economy services like the DoorDash and Postmates for food delivery and the TaskRabbit for everyday tasks. We call this data human-generated spatial temporal data, in short HSTD. Given this enormous amount of HSCD, studying the decision-making behavior for human agents can benefit people in many aspects. For example, studying the behavior of expert taxi drivers can potentially improve the operational efficiency of new drivers. Understanding the decision-making behavior of urban commuters can assist the road network and public transit infrastructure design and resource allocation for the urban planners. Imitation learning is a promising technique to recover human decision-making strategies from HSCD. They model human agent decision-making process as a Markov decision process. In MDP, the reward and policy functions characterize a human agent's decision behavior, which is unknown. Given an expert or very experienced agent's demonstrations, imitation learning aims at learning the reward and policy functions of the expert agent. In this work, we take the passenger-seeking behavior of taxi drivers in a ride-hailing service mode in Shenzhen as an example. Indeed, state-of-the-art IL approaches assume that demonstrations we learn from are obtained from expert agents, which is difficult to guarantee in real-world applications. Taking the taxi drivers as an example, as is shown in this figure A and B, a driver may be more familiar with some particular regions of a city, for example, regions with darker red color in figure A, and therefore has a better performance with higher earning efficiency in these regions due to frequent visits as is shown in the figure B. For these regions, the driver can be viewed as an expert, however, he or she may not have enough experience in other regions of the city where the driver is considered as a non-expert. Similar observations are made in other taxi drivers. As a result, none of existing IL works can provide the optimal policy from the non-expert data like HSTD. Therefore, we are motivated to extract expert knowledge from non-expert demonstrations, which consists of both expert and beginner level demonstrations. Design an algorithm that makes use of them and infer human agents' decision strategies from them. For this objective, we have the following challenges. The first one is how can we quantify the expertise of a human agent at different spatial regions, and how can we disentangle expert knowledge from mixed demonstrations in HSCD, and how to design an IL algorithm such that expert knowledge can be transferred and utilized to learn optimal strategies for non-experts. For the first challenge, we propose an expertise recognition stage. And for the second challenge, we propose an expert knowledge disentangled imitation learning module. And for the third challenge, we find approaches to infer optimal policy for non-experts. So for this first stage, which is expertise recognition, considering different expertise level of a taxi driver in different geographical locations, we partition the Shenzhen map as equal satellite grids showing this figure B, where figure A shows the road map of Shenzhen. Then we quantify the performance of taxi drivers using their demonstrations by their hourly earnings, which we call earning efficiency. Based on observations in prior works, we define an expert grade for a taxi driver at locations where the taxi driver remains high and consistent earning efficiency across time, and the non-expert grades as those that show an obvious increase in earning efficiency with time. Figure C and D shows two taxi drivers earning efficiency in their expert and non-expert grades. We employ generative adversarial imitation learning GALE framework to learn the optimal policy from the expert data that are collected from the expert grades. The generator of GALE is a policy net pi theta parameterized by theta, which consumes the observations of a state and outputs the policy. The discriminator is the reward net R omega parameterized by omega, which takes both the state S and the sampled action A as input and outputs a reward signal which indicates to what degree the generated state action pair matches the demonstrated expert behavior. Meanwhile, in the policynet pi theta, we aim to disentangle the knowledge of the driver into two parts. Specifically, the knowledge related to the specific grades and time slots, and the knowledge irrelevant to the location and time, which is considered as the high-level knowledge of the driver that can be transferred to other locations and time. To accomplish knowledge disentanglement, we designed the PolicyNet as an auto-encoder decoder. To enforce expert knowledge and spatial temporal information disentanglement, we designed a spatial temporal classifier denoted as CLS phi parameterized by phi to classify the location and time information from the hidden latent codes VGT related to gradient time and VK irrelevant to gradient time. The encoder is trained to produce VK as adversary inputs to the classifier CLS phi containing later spatial temporal information and produce VGT as positive samples to promote the performance of the classifier to make correct prediction on spatial temporal information GMT. After we obtain the well-trained net scale model from the expert data, we want to transfer the expert knowledge VK in the expert grade to the targeted state at a non-expert grade. As is shown in this figure, we want to infer the optimal policy for state SNE, which is from the non-expert region or time slot, while SE is the expert state from expert grade and time slot. This expert state SE can be determined by selecting the expert state from the observed data that has a minimum L2 distance to the target non-expert state. Then we utilize the encoder to disentangle the knowledge into VK and VGT for SE and SNE. Then we concatenate the VK of the expert state and the VNEGT of the non-expert state and feed it into the decoder to obtain the optimal policy of the non-expert state. This fulfills non-expert policy inference. We evaluate the performance of our proposed net scale using the real-world taxi trajectory data collected in Shenzhen, China from July to October 2016, for which we compare net scale with baseline methods. We analyze each driver's expertise for each grade via a data-driven approach. Specifically, in the expert grades, an expert driver's earning efficiency remains stable and ranks at the top 15% among all taxi drivers from July to December. The non-expert grades for driver in July are those in which the driver's earning efficiencies increases from July to October and remains stable at the top 15% from October to December from among all drivers. In experiment, we study grades that are non-expert in July and turns expert after October for driver. We use the data from each driver in their July's expert grades to train our proposed net scale model and all the baseline models. And the data in the non-expert grades in July to test the performance of optimal policy inference for the non-experts. Data collected in October in the same grades as the July's non-expert grades are used to extract the ground truth optimal policy for non-experts. The ground truth optimal policy for non-experts are empirically calculated for each grade. Figure A and B shows the KL divergence and L2 distance between the inferred policy and the empirical ground truth policy from the non-expert grades in July. We randomly select 10 drivers from our dataset. The x-axis is the driver ID and the y-axis is the average KL divergence in figure A and the L2 distance in figure B over the non-expert grades for each taxi driver. They illustrate that our proposed net scale outperforms scale and scale in all cases. On average, net scale can reach a 25% and 12% lower Kell divergence comparing with scale and scale respectively, and an average of 33% and 23% lower L2 distance comparing with scale and scale. These results can illustrate that our proposed net-scale framework can outperform the state-of-the-art machine learning approaches in inferring the optimal policy for the non-experts. In conclusion, we propose net-scale, a novel generative adversarial imitation learning for non-experts model that infers expert policy for non-experts by disentangling expert knowledge from their demonstration and transferring the knowledge across spatial temporal regions. Our evaluation results on a real-world large-scale dataset, specifically on taxi drivers' passenger-seeking processes, illustrate that net-scale outperformed the SOTA baseline approaches. And we thank NSF, CIFER-SIM, and ARC for supporting this project. And thank you for your time.